Hi students, welcome to week 3 of the computer architecture session. My name is Anil. I'm going to help you out throughout this GATE 2021 aspirants, especially computer architecture topic. In the previous week, we discussed about single accumulator organization. Just to have a recall, we've been designing a computer system in which we started designing with a processor. In the processor, we started with a register set design, if you could recall. These registers are going to provide you guys the storage provisions within the CPU. Okay, that means that if you want to execute a program, as you all know that the program will be available in the main memory. What is a program? A program is a set of instructions. All the total the total instructions of a program will be residing within the main memory. But when you want to execute the program, you have to execute the instructions one by one. What will execute the instruction? The instructions will be executed by the CPU, but not by the main memory. So for that, we need to transfer these instructions into the CPU for execution. So if you want to store the instruction which is being executed concurrently, we do require something called a register set. The register set is going to store the currently executing instruction with the associated data, as we already discussed in the previous week. Now, in this week, I am going to take you guys to the next register organization. In fact, if you could recollect, we started with single accumulator organization, right? Single accumulator organization. Again, what are the different registers that we do have in a single accumulator organization? In the single accumulator organization, we do have the registers like the program counter, address register, instruction register, data register, accumulator. I'm calling it as ACC. ACC stands for accumulator. There is something called temporary register. There is something called input register, and there is something called output register. Last week, we discussed about the significance of each and every register here, didn't we? Yes, we discussed about the purpose of each and every register which showcased here. Okay, for an example, when it comes to the program counter is going to store the address part of the next instruction. Next instruction's address, let me call it as. Address register is going to store any address that is needed to be located within the main memory. So, if you could look at each and every register here, each and every register is going to store some specific data. Okay, because all these registers are specially designed to store only a specific data. For an example, when it comes to the program counter, can the program counter store any other thing than the address part of the next instruction? No. Okay. When it comes to the address register, it is only going to store the addresses that are going to be sent to the main memory for locating the data. When it comes to the instruction register is only going to store the current instruction. Yeah, as you can look at each and every register here, each and every register is specially designed to hold a specific data. Okay, that is all about single accumulator organization. In the single accumulator organization, totally we do have 8 different registers. Each and every register is going to be designed is designed for a specific purpose rather. Okay. Now, as you guys know that there are two more register organizations. Okay. If you could recall what happened in the previous week, there are three different register organizations. Register organizations I have stated as the first one is single accumulator, second one is general register, and the third one is stack organization. Okay. So far till now we discussed about single accumulator organization. Yes, right? Now let me make it very simple about general register organization. Second one is a general register organization. I will make it very simple. I will make it very easy for you people if you could properly focus here. Okay. The difference between single accumulator organization and general register organization, I am telling you right now. Listen to me very carefully. Okay. In general register organization, in addition to the the registers that are available in a single accumulator organization, we do have several other registers. Okay, let me show here. Yeah, now it will be done in 2 minutes. If you want to understand general register organization, stay focused. In general register organization, sir, what is the difference? Simple. In addition to all these registers, we do have several other registers. Okay. Now, let us understand what these registers are going to store. What these registers are going to store. In fact, when it comes to the single accumulator organization, each and every register is going to store some specific amount of data, right? Some specific data. That is, program counter just stores the address part of the next instruction. Okay. In general list organization, these additional registers that are present here are going to store any data, any general purpose data. This is the only difference. Okay. That is, in a nutshell, if you want to simply talk about general list organization, in general list organization, we are going to have some additional registers along with the registers that are available in the single accumulator organization. These registers, these additional registers are purely for general purpose. That is R1, R2, R3, R4. I am not naming it as any specific, I am not using any specific naming convention to name these registers. Okay, simply I am naming these registers as R1, R2, R3, R4, R5, whatever, R6, R7. That means that these registers can take any data. It could be an address, or it could be an operand, it could be instruction, rather it could be a temporary data. There is no restriction. There is no restriction on the data that is needed to be stored in these additional registers in the general register organization. That is the only difference between single accumulator and general register organization. Okay. Now, you could ask me, sir, what is the total number of registers here? In single accumulator organization, there are 8 special purpose registers. That is program counter, address register, instruction register, data register, accumulator, temporary register, input register and output register. Okay, fine. These are 8. But in general register organization, how many general purpose registers available in a system? My answer is, that depends on the system. When it comes to 8086, okay, I think you might have heard about these numbers. 8086. What are these numbers? This is nothing but a processor. As you people know that 8086 is a processor. Next processor is, let us say, IA32. What is IA32? IA32 is the next generation processor to 8086. In 8086, there are a total of 7 general purpose registers which can hold any of the data. In IA32, I do have, no. IA32 has 16 general purpose registers. Okay. And these number of registers will be different from processor to processor. Okay. So that is the difference between single accumulator organization and general register organization. Okay. Yeah. Good. Lokesh Pranab, of course, this number 8086 is just nothing but a processor. Okay. Now, let me ask you a question. Stay focused. You are executing a program. Okay. Whoever it is participating here, somebody is called Lokesh Pranab or RK classes. Somebody else is there. Okay, fine. I do have a question for you guys. That is, when you are executing a program, you declare a variable. Let us say, I'll write it here. You declared a variable a is equal to 10. Okay. After declaring this variable, then in some instruction, you are going to use this variable. Okay. That is a plus plus. You are going to execute one instruction called a plus plus. In what way it is going to execute? Okay. That means, as you already know that a is just nothing but a memory location. Okay. The moment you declare a variable, a memory location will be allocated, will be allotted, whatever. That address of the memory location may be, let us say, 250. The processor decides to allot an address 250 for this variable that you declared. After which, when you initialize the variable with a value, that value will be transferred to that specific memory location, right? Now you want to increment this variable. That is, in an instruction, you specified that a plus plus. What is a plus plus? A plus plus means that a is equal to a plus 1. Got me? So, if you want to perform a is equal to a plus 1, what will happen inside the processor? That is my question. In what way the variable a is going to get incremented? That is my question. Yep, you interpreted right. If you want to increment this, what will happen initially is the variable a will be assigned to a processor's register. For an example, in the general register organization, if you want to execute a plus plus, that is incrementing the value of a, the processor is going to allot a processor's register for a. Now, in this case, let us say that the processor decided to give R3 to A. That means the A value will be transferred to R3. That means that A's equivalent register in the processor is R3. Okay. So R3 value will be equal to 10. Again, if you want to increment a variable, first of all, that variable must be transferred to a processor's register. Okay. After which, any of the updations must be performed within the processor's register. Finally, after updation, the value can be transferred back to the variable, that is A. I hope you got it. Once again, the rule is, every time when you want to update a variable, initially the variable will be transferred to the processor's register, one of the processor's register. After which, the contents of the processor's register will get updated. Okay. After which, finally, the value of the processor's register will get transferred back to the variable. This is what every time gonna happen when you want to update a variable. Okay, so here you can understand the importance of general purpose register. For an example, if you want to perform A is equal to B plus C, okay, here A, B, C are three different variables, which means that I do require three different registers within the processor, right? Okay, so general register organization will give you more flexibility and advantage of having more number of registers which are needed to execute your program, especially when variables are getting updated within your program. That is because every time when you are going to execute a program, there are several variables. Let me put it here. There are several variables. Okay. When I write a program, I do have a set of variables. This is my total number of variables. Okay. I do have, let us say, 18 variables. Altogether, my program has a total of 18 variables. Now, each and every variable of my program are going to get updated, get updated during some time of the execution of the program, right? During which that particular variable will get transferred to one of these registers. Okay, after the updation, then the contents of the register will get transferred back to the variable. This is the importance and the advantage of the general register organization. So this is the thing with the general register organization. So what did you learn? What is the difference between single accumulator organization and the general register organization? In a single accumulator organization, we do have only 8 special purpose registers. But in general register organization, in addition to these special purpose registers, we do have a few more general purpose registers, which are going to be helpful to accommodate the variables whenever they are getting updated. So this is the thing with the general register organization. Okay. Now, fine. If you want to understand a general register organization, it is very simple, as I already told you. Now let me take you people into the world of stack. Let me explain you people about the concept of the stack completely. Now, before getting into the details of the stack, my request, rather whatever you call it as, my request for you people is to forget the details what you already know about a stack. Okay, that is when you are in your C programming or C++ programming, when you are executing some programs, you might have heard about a stack. Rather, you might have constructed a few programs by using stack. Okay, now in this class I am going to give you another dimension of the stack. So far you know about a stack from the programmer's point of view. Yes or no? You know about a stack. That's as maximum as the stack is a linear data structure, which is a LIFO data structure in which the element which is pushed last is going to be popped out first. Other than that, the details that you know about a stack are minimal and limited. Now, let me tell you, after this class, you're going to get the complete details, how the stack is designed, the design architecture of the stack. You're going to completely understand. Okay, now we are not using the stack. We are designing the stack. Now we are the designers of the stack. So far, what you did, you just use the stack which has already been designed by the computer architect, right? Now we are going to design the stack. Okay, now let me explain you how am I gonna design a stack. If you want to understand completely about a stack, the first thing that you need to understand is every processor requires a stack. Every processor needs a stack. Okay. Sir, why the stack is required? What is the usage of the stack? What are the applications of the stack? Forget about all those things. We are going to discuss about the applications of the stack once after we design the stack. Okay. Now let us straight away design the stack. Now ignore the applications of the stack. Why the stack is used? Why stack has to be involved in a computer system? Those details let us ignore a bit. Okay, for some time. Let me start with the types of the stack. If you want to get into the details of the stack, there are two different types of the stack. One is a register stack. Important, stay focused carefully. If I have questions, you need to answer. That's it. There is no other go. A register stack, and the second thing is a memory stack. Okay. First thing is the register stack, and the second one is something called a memory stack. What is the difference? When it comes to stack, stack is of two types. One is a register stack and one more is a memory stack. What is the difference? Simple. The difference is the register stack will be available within the processor. The register stack is available within the processor. Okay. The memory stack is available in main memory. So being a designer, when you want to design a computer system, you need to design two different kinds of a stack. The first stack is the register stack. You design one stack and put it in the processor, which will be called as the register stack. You design another stack and store it in the main memory. You put it in the main memory, which is called a memory stack. Okay. Now let me tell you something. That is, we do have only one register stack. Only one register stack. That is, every processor will have a single register stack. Okay. But in memory, there will be multiple stacks. It is not limited to only one. In memory, there are several stacks. Why I do require multiple stacks? Just recall your operating system's concept here. You people might have heard about every program or a process requires its own and dedicated stack. Yes or no? You might have heard, you might have learned that every program that you write or every process. Program is a generalized name. A process is an operating system's name which is given to a program. Okay. And I'm not going to state any difference between program and a process. Both are one and the same. Being an architect, I'm not going to get into the details of the operating systems. For this instance, program or process is one and the same. So every program or a process requires its own and dedicated stack. I think you know about it. Do you or not? I want answers. Logesh Pranav and Modulus Mind, RK classes. I want answers here. Do you know that every process do require its own and specific stack, dedicated stack? Yeah. As you know that, we do require a specific stack and a dedicated stack for every process. Which means that in main memory, we do have multiple stacks. Each is dedicated to a process, its own process. If I do have, let us say that 50 programs that are available concurrently in the main memory, 50 programs that are loaded in the main memory currently, each and every program will have its own stack, which means that I do require to have 50 stacks at this time in the main memory. So which means that register stack will be only one, because in a processor we have a limited space. Which can accommodate only one register stack. But memory stacks are multiple. because each and every process that is available in the main memory requires its own and dedicated stack. Okay, yeah. Now let us design initially a register stack. Now let us design a register stack. What is the register stack? This stack is available within the CPU itself. This stack has been designed and embedded to the CPU. Okay. Now let me design a register stack. I am designing a register stack. Okay. Yeah. Let us say that I designed an 8-element register stack. This is in the processor right now. Okay. Now, before we come and discuss about the stack, we need to discuss about a few guys who are related to the stack. These people that we are going to discuss right now are associated with the stack. So here the associated guys to the stack are, the first one is something called a stack pointer. We talk about these guys later. The guys who are associated to the stack are as follows. The first one is a stack pointer. The second one is something called a data register. And the third one is something called full, which is the 1-bit register. The fourth guy is something called empty, which is another 1-bit register. Fifth guy is something called a push, and the remaining one is something called a pop. Okay, all these guys are related to stack. Okay, let us discuss about the significance and the importance, the purpose of each and every guy here. The first component is something called a stack pointer. The stack pointer, what is a stack pointer? The stack pointer is just nothing but a register which is going to hold the top of the stack. Okay, the address of the top of the stack. Okay, let me label it. This is 8-element stack. This is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 1, 1, 0, 1, 1, 1. Okay, so here stack pointer points to the top of the stack or head of the stack or whatever. Fine. Here I do have my stack size is 8-element stack. It's an 8-element stack. It's an 8-element stack. Okay. Here each and every location of the stack has an address. 000 is the first address. 111 is the final address. Okay. Here the thing is, the stack pointer, for an example, currently there are 1, 2, 3, 4, 5 elements are present in the stack. That means that in 100 I do have an element. For an example, okay, element 1, element 2, element 3. So there are 5 elements in the stack. Topmost element is present in this location. Okay, the time stack pointer is going to show 100. SP will be here. Okay, which means that the stack pointer shows the address of the topmost element of the stack. In this case, in the address 4, there is a topmost element. That means that the stack has 4 elements. So the topmost element's address is 4. Of course, there is no need to prolong it because most of you guys already know what is a stack pointer. stack pointer is going to hold the address of the topmost element of the stack. That's it. Okay. Next comes to the data register. What is this data register? This data register is the source as well as the destination for the data of the stack. If you want to push an element into the stack, the element must be collected from the data register and pushed into the stack. If you want to pop out an element from the stack, the element that is popped out from the stack, out of the stack, will get transferred to the data register. I hope you got the point. The contents of the data is originated at the data register, which means that if you want to send an element into the stack, first the element must be made available in the data register, because we are going to collect the element from the data register and push it into the stack. Okay, and when you want to pop an element out of the stack, the element which is popped out will get transferred to the data register. Okay, so that is all about the data register. What is full and what is empty? Of course, as you know that when full is equal to 1, the stack is full. Okay, when full is equal to 1, stack is completely full. You can't push any more element into the stack. So before we push any data element, we need to check out with this. We need to check out with this full flag. What is this full? Full is a 1-bit register which is called as a full flag. When it is equal to 1, it is going to state the status of this flag when it is full, if it is full. Okay. What is empty? If empty is equal to 1, means that the stack is completely empty. So if you want to pop out an element of the stack, you need to check with empty. If it is empty, you can't pop any element out of the stack because stack is completely empty. What you're gonna pop out? Okay, so if you want to push an element, check with full flag. If full flag is equal to 1, you can't push any more element into the stack because stack is completely full. If you want to pop out an element, you need to check with the empty flag, because if the stack is empty, you cannot be able to pop out any element out of the stack since it is empty. Okay, of course, as you know that push and pop are the operations that are associated to the stack. Okay, there are only 2 operations that are possible. If you want to organize the data within the stack, you can use only 2 operations. One is push and one more is pop. Okay, and one more thing is, no matter how many elements that are present in the stack, only one element that is visible to a programmer, that is the top of the stack. Okay, for an example, stack is completely full. Can you access any element directly? No, you cannot access any element directly. Rather, only one element will be available for the programmer, that is the top of the stack. Okay, at any point of period, only one thing that can be retrieved out of the stack is stack pointer, that is the top of the stack. That's it. Okay, now let me tell you, let us get into the details, more design details of the stack. Okay, stay focused here. Now I want to perform a push operation. Let us say just the computer has been switched off, which means that the stack is completely empty. Absolutely there is no element in the stack. Now I want to push one element into the stack. Okay, this is my question to you guys. I do have 8 elements, 000 to 111. Initially the stack pointer will show 000, right? Initially, when there is no element present in the stack pointer is going to show 000, because this is the first address of the stack. Now my question is, when I am going to push the first element into the stack, where it is going to be pushed? When an element has to be pushed into the stack when the stack is empty, where it is going to be pushed? Which location? In which location the first element is going to be pushed? This one or this one? 000 or 001? That is my question. I will wait for your answer. Okay. Logesh, perhaps 000 is not the answer. Okay. Listen to me carefully. Every time when you want to perform a push operation, what will happen to the stack pointer? Stack pointer will get incremented. Okay. When you want to perform a push operation, okay, this push operation is involved in this sub operation. The first sub operation that is going to be performed when you want to push an element into the stack is first stack pointer will get incremented. SP is equal to SP plus 1, which means that stack pointer will go here. Which means that stack pointer will go here. Okay. After pushing it, the element will be placed at the stack pointer. Okay. So the first element is going to be pushed in 001. Here element 1, I will say EL1, which means that the first element of the stack is going to be pushed in 001, but not in 000, because every time when you want to perform a push operation, understand carefully, first stack pointer will get incremented. Okay, then in the incremented address, the element will be pushed. Why also I'll tell you. Okay, for an example, you told me that, let us consider that scenario also. Okay, here this is 000, this is a 001. According to you, and initially, of course, stack pointer, everybody knows that will point to the base element, that is 000. Got me? Now, according to you, it will be pushed here, right? The first element is going to be pushed here. For an example, let us consider your thing that, of course, what you said, Lokesh Parab told me that the first element gets stored here, EL1. Then everybody knows that during every push operation, stack pointer will get incremented, right? Yeah, you pushed an element, then you incremented stack pointer. You can clearly see this is contradicting the rule of the stack pointer. What stack pointer should show? Stack pointer should show the topmost element, but here stack pointer is showing some null element. 001 is not the topmost element of the stack, because 001 doesn't hold any element, right? I hope you got the point. Okay. Once again, when you want to perform a push operation, first stack pointer will get incremented, then it will be pushed, not in the 000 address. Okay. I hope you got it. So every time when you want to push an element, initially stack pointer will get incremented. In the incremented label, in the incremented location, then the element will get pushed. Okay, so obviously the element 1 will not get pushed here, rather the element 1 will get pushed into 001. So this is element 1. Okay, obviously second element goes here, third element will go here, will go here, fourth element goes here, 1 2 sorry, this is the third element, this is the fourth element, fifth element goes here, sixth element goes here, seventh element goes here, right? Which means that every time when you perform a push operation, if you want to push the second element, stack pointer will get incremented, element 2 will get pushed. stack pointer will get incremented, element 3 will get pushed. Similarly, after performing all the push operation, stack pointer finally here, right? Stack pointer will be finally at triple 1. Okay, so element 7, there are a total of 7 elements have been pushed into the stack right now. Yes or no? My question is here, still this element is not, no, this location is not filled due to the logic of pushing an element into the stack, right? That means that we are unable to use this 000th location. Yes or no? We are unable to use this 000th location because of the design logic, pushing logic. Initially, stack pointer will be pointing here, and if you want to push an element first from 000 to 001, stack pointer will get incremented, will be updated, after which element will get pushed. So finally, during this process, stack pointer comes to 111, which is the topmost address of the stack. Yes or no? In which element 7 has been pushed. Did you get it? Now the problem is, we are still left with one more empty location of the stack, which is 000th location. Yes or no? Shall we be able to use it? Shall we be able to use it? Or can we not use it? This is my question. I hope you got it. Simple. According to the stack that you have watched here, the stack is now filled with only 7 elements. 000 element is not, means 000th location hasn't been filled up with any data, because initially when you want to push an element, stack pointer should be incremented and pushed. Due to this logic, 000 hasn't been utilized at all. Can we use 000 element? Rather, cannot be. I will tell you. Okay. Forget about this. Forget about this stack for a while. I'm not gonna talk about this stack. Let us understand how. Okay. Lokesh Pranab, how we can't use. Okay. Fine. Lokesh Pranab, you told me that we can't use. Fine. Let me admit some things before I talk about whether we gonna use it or not. Whether we are able to use this 000th element or not. For an example, you are designing something, okay? No matter whatever you are designing, let us say you are designing a chair, you are designing a sofa, you are designing a cot, whatever you are a designer in the world, you are going to design the real world entities. It could be a chair, it could be a sofa, or it could be a bed, okay? For an example, you design a bed which can accommodate 4 people, okay? You designed a bed which can accommodate 4 people. Rather, you design a sofa which can accommodate 4 people, and after design, if the sofa is able to accommodate only 3 people, do you take it? Obviously we don't, because if you are a designer, you will ensure that the thing what you have designed will be utilized to its potential. Yes or no? That to the total capacity it must be used. Yes or no? Either it could be anything. It could be a stack, or it could be a bed, or it could be a chair, or whatever. If you are a designer in the world, before designing itself, you will ensure that whatever you are designing will be utilized to its total potential, not to just a half. Rather, you're not going to leave any of those slots, right? Clearly, even in the stack, the designer will think the same. Okay, according to the logic, you might think that 000 can never be utilized. But if that is the case, every stack is going to waste one element. Every stack is going to be designed at a cost of one element. No, it is not true at all. Still, we are going to use 000. Okay, how? Let me tell you. Stay focused very carefully. Okay, now what is the size of the stack pointer? Size of the stack pointer is 3 digits. What is a stack pointer? Let me tell you. Stack pointer is just nothing but a register, right? What is a register? A register is a collection of flip-flops. Okay, what is the size of the register? Size of the stack pointer is 3 bits. Yes or no? which means that in order to design my stack pointer, okay, for a stack which is going to hold 8 elements, the stack pointer size must be equal to 3 digits, right? So because from 000 to 111, any of the locations of the stack can be addressed. Okay, so try to understand. Initially, stack pointer is equal to 000. If you want to push an element, stack pointer is equal to stack pointer plus 1. So it will go to 001. At 001, element will get pushed. Finally, we will reach to an address which is, supposed to be the top of the stack, because 111, as you can clearly see, is the topmost element of the stack. Rather, the address of the topmost element of the stack, that is 111. So after you push the element 7 at 111, still there is 000 left. Yes or no? Stay focused. Still you can push one more element. How? At 111, if you want to perform one more push operation, what you need to do? Initially, you need to increment the stack pointer. Yes or no? Yes. You are going to increment the stack pointer. Let me tell you. When you increment the stack pointer, 111 plus 1 is equal to obviously 000. Yes or no? 111 plus 1 is equal to obviously 000. You don't tell me, sir, it is 1000. Because the size of the stack pointer is finite. When it is finite, it will get discarded. Okay. The next, what you call the overflow or carry, whatever it is, it will get discarded. Did I make it myself clear? Absolutely correct. 111 plus 1 is equal to 000. When you increment the stack pointer at 111, it will come back to 000, in which the final element of the stack will get pushed. Did I make it myself clear? I hope you understand this, didn't you? Mr. Parab, are you there? Good. Very good. So, this is what the design logic of the stack. This is a CPU stack. So, let me tell you the sub operations. Write down somewhere. I'm gonna give you every time when you being a programmer, just think right. Parab, you consider that you're a programmer. Now you're performing a push operation. In being a programmer, if you want to perform a push operation, what you will write? Simply, you're going to write an instruction called push, right? Okay. Every time when you execute this instruction push, what is going to happen inside? Okay, let us stay focused. A push operation is of the following sub operation. The first operation of the push instruction is incrementing the stack pointer. Stack pointer will be equal to SP plus 1. After incrementing, what we need to do? We need to push where the data is available. Yes, the data is available in the data register. From the data register to memory of the stack pointer, right? Memory of the stack pointer element will get pushed. So initially it gets pushed to 00001. So the stack pointer is 001. 001 is just nothing but an address. So the memory location is this one. So which means that the contents of the data register will get pushed into the memory of the stack pointer. Okay. This is the second operation. This is the first operation. This is the second operation. And the third one is during every push operation, rather after performing the push operation, we need to watch if the stack is full. Yes or no? After push operation, it is quite possible that stack may be completely full. If it is completely full, being a designer, we need to set the bit in this flag register, because every time when the stack is completely full will be equal to 1. Who is going to set this bit? Being a designer, we should be able to set this bit, right? Now we are the designers. We are not going to leave anything to anybody. We are going to see to that this full will be equal to 1 when the stack is completely full, right? Yes. That means that after push operation, you just see if the stack pointer is equal to 0. if SP equal to 0. Why SP is equal to 0? Where the final element is being pushed? The final element is being pushed at 000. Yes or no? Okay. Which means that after a push operation, if stack pointer reaches to 0, then the stack is full. That means that we need to check the condition if the stack is full in such a way that after a push operation, check just with if SP is equal to 0. If SP is equal to 0, then full will be equal to 1. Did I make it myself clear? Very good. No. If full is equal to what? Full is equal to 0. Yeah, if full is equal to 0. Yeah, Lokesh Parab, you're absolutely right. Hold on for a while. Let me tell you. Now, we incremented. We push one thing. So, SP is equal to SP plus 1. After which the contents of the data register gets pushed into the stack. After pushing it, we need to check with if the stack pointer is, if the stack is completely full. Because during every push operation, we need to check it. After push operation, it is quite possible that the stack might be completely full. So during every push operation, you need to check if the stack is full. During every pop operation, you need to check if the stack is empty. So what we performed? We just performed a push operation. So what is the responsibility? We need to check if the stack is full. How are we going to check? If the stack pointer reaches to 0 after performing a push operation, then full will be equal to 1. Yes or no? Did I make it myself clear, Lokesh? Did you get it? After final push operation, where stack pointer is locating? What stack pointer is holding? Stack pointer is holding 000. Yes or no? Good. Okay. So, if the stack pointer is equal to 0 after performing a push operation, then full is equal to 1. If the full is equal to 1, being a programmer, we do have one more thing in our one more responsibility on our shoulders, that is we need to ensure that empty is equal to 0. Did I make it myself clear? Either full or empty, only one could be 1 at a time, but not both, right? So when full is equal to 1, you ensure that you set this empty digit to 0. Got me? Got me? Good. Now, let us perform a pop operation. Okay, simple. The pop operation, on the other hand, works as follows. In the push operation, what we're doing? In the push operation, first we are incrementing the stack pointer, then we are pushing the element. But in the pop, what we're going to do? First you pop the things up. That is, send the content initially to data register. Memory of the stack pointer to the data register. Do not update the stack pointer initially. Okay. What you're going to pop? Whatever that is available at the topmost, as a topmost element, at the topmost location must be popped, right? So, you should not update the stack pointer initially during a pop operation. Initially, first you send the data element to the data register, which is available at the topmost element of the stack, at the topmost location of the stack rather, after which then decrement the stack pointer. SP should be decremented. SP is equal to SP minus 1. So here you can clearly see, of course I don't need to tell you, initially what we do is, during a pop option, let us say stack is completely full. Now stack pointer is equal to 000. At 000 element 8 is present. What we are going to retrieve? Element 8 we are going to retrieve as the first thing, right? So because it is pushed most recently. Now when you perform a pop operation, memory of the stack pointer. What is stack pointer? Stack pointer is 000. What is the element? Element is equal to 8. Will get transferred to data register. After pop operation, what should we do? We should decrement the stack pointer. SP is equal to SP minus 1. I think I don't need to tell you how 000 minus 1 is equal to 111. I hope you got it. I don't need to explain that simple detail. 000 minus 1 will take you to 111 because of the quantum borrow method. there is something called quantum borrow. We are going to assume that there is one more digit available. From that, we are going to take a borrow. After taking the borrow, 000 minus 1 will be equal to 111. Okay, so stack pointer has been decremented. Then what we'll do after pop operation, what we need to check? What is the responsibility? What is the overhead? We need to check with. If the stack is empty, yes or no. How are we going to check it? Again, if SP equal to 0 after a pop operation, then empty is equal to 1, full is equal to 0. Okay. Simply. Okay, because either after stack is completely full or after the stack is completely empty, 000 is the base of the stack. Either it is the top of the stack or it is the base of the stack. Okay, so initial top of the stack or final top of the stack is 000 only. Okay, so initially you get this element, you go to 111. Finally, after performing a final pop operation, where you will come? You will come to 000 only. Yes or no? Because let us say element 1 will be the final one that you are going to pop. After popping this, 001 minus 1 will be equal to 000. So you can understand here, that is 000 is the initial and final top of the stack. Okay. So likewise, we are going to design a register stack. These are the sub operations. Rather, you can also call them as a micro operations. During every push operation or a pop operation initiated by the programmer. Did I make myself clear? Any questions so far? Because next week I'm going to explain you guys about a memory stack. Okay, I think it might give you an insight view of a stack. So far, what you know about a stack. What is a stack? Simply, it's a linear data structure. What is a linear data structure? Simple, last in first out or first in last out. Other than that, we do not know the design logics of the stack, right? Okay, so after this, I do not want you people, I do not have you people having any doubts in your mind during a register stack. A register stack is a stack implemented within the processor's registers. We are going to collect a few registers to design the stack. In order to design an 8-element stack, I need to have 8 registers collected and organize it as a stack. Okay. Now the size of the stack can be as much as you want. It could be 16-element stack or it could be 64-element stack. But only the thing is, you need to have the provision of 64 locations to design that stack. Did I make it myself clear, Parag? Yeah. Okay. So next week, as I told you in the initial session, rather in the beginning of the class, there is something called a memory stack also. Not only a single memory stack, as I told you that we do have a multiple memory stacks, right? How to design a memory stack? We're gonna see it in the very next week. So don't miss, because I'm going to take you to the insight view and the different dimension of the stack. Okay, which is pretty much useful in the advanced computer architecture, because the gate when you attempt a gate, when you're an aspirant of gate, just forget about your university exams. Gate is going to test you at a subject level. Okay, you are going to get into the insight depth of the subject. Okay, so next week what we're going to discuss? We're going to discuss about a memory stack at a different level. Okay, so that's it for the day. We're going to see you next week.